Alright, so in this video I'm gonna be explaining another important article with the title Graph Clustering with Graph Neural Networks. So this paper in 2023 in JMLR. Graph neural networks have achieved state-of-the-art results in many graph analysis tasks such as node classification and link prediction. However, important unsupervised problems on graphs such as graph clustering have proved more resistant to advances in GNNs. Graph clustering has the same overall goal as node pooling. Does this mean that GNN pooling methods do a good job at clustering graphs? The answer is no. Current GNN pooling methods often fail to recover the cluster structure in cases where simple baselines such as k-means applied on learned representations work well. So we investigate further by carefully designing a set of experiments to study different signal-to-noise scenarios, both in graph structure and attribute data. So because of this, we are talking about graph signal processing, which is a field of study. To address these methods, poor performance in clustering, we introduced deep modularity network, an unsupervised pooling method inspired by the modularity measure of clustering quality, and show how it tackles recovery of the challenging clustering structure of real-world graphs. Similarly, we showed that Daemon produces high-quality clusters, which correlate strongly with ground truth labels, achieving state-of-the-art results over 40% improvement over the other pooling methods across different metrics. So most existing work on GNNs to leverage high-order structures does not directly address node partitioning or cluster assignments within the computational graph. So you see the related work in terms of 6 desirable clustering properties. And Daemon passes all of them because it is end-to-end, it is unsupervised, it has node pooling, it is sparse, it has soft assignment, and it is stable with low computational complexity. Node aggregation is crucial for our interpretation of graph pooling in terms of clustering. So both top K and SAG pooling that I've explained in different videos, they only sparsify the graph and do not reduce the node set. So we have graph of n nodes and m edges, and we are interested in measuring the quality of graph partitioning F that splits the sets of nodes into K partitions. So in contrast to standard graph clustering, we are also provided with node attributes. So X is given. So cut-based metrics, I have explained it in min-cut pool in a different video, but this approach of this paper is different. It uses modularity, which comes from community detection, literature. that measures the divergence between the intra-cluster edges from the expected one. So this paper, we cannot say it is. So let's carry on. Modularity measures the divergence. So we want the expected number of edges to be very different from the number of edges inside each cluster. And we represent it easily using trace of C transpose BC. And C is just a cluster assignment matrix. But B is related to the adjacency and the degrees. So B is a dense matrix. While B is dense, iterative eigenvalue solvers can take advantage of the fact that B is a sum of a sparse A and a rank 1 matrix, meaning that the matrix vector product can be computed efficiently like this. For example, you can use Lanczos algorithms to solve it efficiently. And about graph neural networks, so for example, graph convolution, we updated the features. But how do you want to find the cluster assignment C? The input to the cluster assignment can be any differential message passing, but we especially consider the case where a graph convolution is used. So again, we used like diffpool, if you remember, they also used graph convolution to get their cluster assignment. And so we have modularity and the collapse regularization. So it combines insights from this spectral modularity maximization and a novel regularization. This is the regularization that prevents trivial solutions to the optimization. Because if we don't have this, then solution becomes very trivial, and that is not what we are investigating. So we decompose the computation as a sum of sparse matrix multiplication and rank 1 degree normalization. Without additional constraint on assignment matrix, spectral clustering for both mean cut and modularity has a spurious local minima. Assigning all nodes to the same cluster produces a trivial locally optimal solution that traps gradient-based optimization methods. Mean cut pool addresses the problem. For example, in that video, mean cut pool, I said that we can have soft orthogonality regularization to avoid such trivial cases. And you see that they have better training if you use their approach in comparison to mean cut pool. So they tried on benchmarks like Quora, CiteSeer, PubMed. Of course, most of them, these are homophilious, not heterophilous graphs. So they are simple. That's why you have high. There is a measure of homophily. It's more than 80% homophily. So these datasets are really easy. That's why you get high node classification scores. And of course, they compare it with k-means and different traditional methods for clustering.